So, good morning. Welcome to Krishna's classroom. We continue with our exploration of the class of measurable sets. In this context, we have seen that there exist non-measurable sets, and therefore the measurable sets do not constitute the entire set of all subsets of the real line. And having resolved that, then we found that there exists uncountable measurable sets whose measure is 0. Now we explore another problem. You know that I use the Venn diagram again. So I consider this as PR, a set of all subsets of the real line, which forms a sigma algebra, which is the largest sigma algebra that you can constitute with subsets of R. Now we have seen that the measurable class script M is a subcollection of this because there exists non-measurable sets. Further, we have seen that all open sets are measurable. Therefore, the smallest sigma algebra that contains the open sets is measurable. Okay, and this collection is what you call the Borel sets. Now, it's not very clear at this stage whether the Borel sets constitute the entire M or not. Okay. So, what we are going to prove is that the Borel sets, which are measurable, form a subcollection of the class of measurable sets. That means there exists non-Borel measurable set or measurable subset of R. Okay. So we need to. So that means we are structurally exploring what measurable sets are. Right. Now, one significance of the Borel sets is that it is the open sets constitute what is called the usual topology of R. Therefore, the minimal collection of or minimal sigma algebra that contains all the open sets which constitute the usual topology of R is what we have denoted by Borel sets. And what we are going to prove is that there are some sets which do not belong to this, however, they are measured. Now this needs some work. So we begin with, we use the Cantor-Lebesgue function and its properties. To resolve this question. That's how. So this is what we do. Thank you so much. Okay, as usual, we shall construct a new function psi. Already recall the graph of the Lebesgue function. Now we are going to modify this and construct a new function. Okay. So let we prove the following theorem. Let phi be the Cantor function on the interval 0, 1 and define rather define a new function psi on 0, 1 by for every x it's a very interesting. Then we prove the following properties. Then psi is strictly increasing continuous which maps zero. Further, we have the following property. The first property is that psi maps the Cantor set C onto a set of you know that the Cantor set has measure 0. Therefore, this is something. Second property is that psi maps a measurable set to onto a now this measurable set is a subset of C. The countersets. So this is the result that we try to. So let us prove this. Very nice result, which gives some insight into the nature of measurable sets, Lebesgue measurable sets. Okay, so proof. Now, psi is continuous because it is the sum of two continuous functions being a sum of two continuous functions. That's the first thing that we observe. We'll look at the definition of this. Okay. Now, psi is strictly increasing. Recall that phi is increasing. It maps 0, 1 to 0, 1. Now what happens is that psi is actually psi of x equal to phi of x plus x. Now you see that there are sets on which phi of x is a constant, because you see that the entire O, okay, on each of the components of O, you see that the phi is a constant, okay, right? So on each of the interval components of O, right, it's a constant. So what makes this strictly increasing is this function. You know that this function, that is say chi x equal to x, is a strictly increasing function. Okay, now it's quite easy to prove that this is so, right? So I leave it as an exercise. Now this is trivial. Strictly function and phi x is an increasing. That's observation. Now therefore what you have is that psi is, now you can easily see that psi of 0 is equal to 0, psi of 1 equal to 0 is equal to 2, and psi is continuous monotonically or strictly increasing. Therefore, you see that it attains all the intermediate values between 0 and 2. Continuous and hence attains all intermediate values of 0 to at 0 to exactly so there is one and only one value of x on the interval 0 1 which gets mapped to a given point on 0 2, and for each point in 0 2 there is a corresponding point on the interval 0 1 whose image under psi is the given. So psi is a bijection from this is the conclusion. Okay. Now you see that O is, as we have defined, this is the interval 0 1 slash the Cantor set. It's a complement of the Cantor set, the interval 0 1. Therefore, which is a disjoint so this result will, okay, therefore psi 1 to 1 and on to now implies zero to is equal to psi of 0 1, and that is essentially psi of C union O is equal to psi of C union psi of, this is easy to see. You can show that there exists no common point between psi C and psi of O. This is not 0, this is O. This is 0. This is O. This is again. So this is the outcome of that. What does it mean? It means that psi has an inverse, and not only that, psi has a continuous. This from and is continuous. That's easy. Okay, from what we have worked out, you can show that that implies psi of C is closed and psi of O is open. That's also easy, right? Therefore, both psi of C and psi of O are measurable subsets of okay. That is because closed sets and open sets are measurable subsets. So what next? Now we claim that, and so the question is, what are the effect measures of you know that the measure of this is equal to now you see that O is a countable disjoint union of open intervals ik. 1 to infinity, where some enumeration of these open intervals. And they are disjoint. I mean, to recall the collection, how we constructed O, what did we do? First started with deleting the middle one third of the interval 0, 1, and then the leftover closed intervals, it deleted the middle one third, and so on. So it's a countable collection, and you see that this IKs belong to these deleted open intervals. And we know the length of each of these IK and their sum. So what we have is this, that O is okay, it's a disjoint union of open intervals, and therefore to see that now we want to know what exactly is this is what we are measure of this is what we are interested. So we have to find out psi O. Okay. Now you see that what about phi? Phi is constant on each of I. And psi is monotonically strictly increasing. Okay. Therefore, to see that, what about psi of ik? Psi of ik is an interval. Okay, so psi phi and a monotone, a strictly psi of ik is an interval. And therefore, what you have? You have length of ik equal to length of ik. This is because since that's the reason. Therefore, it's a length invariant maps to another interval. Ik is mapped onto another interval in the range space 0 to 2 of length the same as the length of ik. That's easy to from the definition. Okay. Psi of ik is a disjoint collection of intervals whose union psi o So we have the following. Now we have all the ingredients to find the measure of psi. So measure of is equal to sigma k equal to 1 to the length of, because it's an interval, psi of I. And this we have already seen that length of psi of ik is length of ik. And this is since O is equal to the union of the disjoint union of this intervals ik, this is equal to of okay, and measure of C is equal to 0. Measure of equal to 1 and O is equal to the Cantor set. Therefore, C, which is equal to, therefore measure of psi O equal to measure. Okay. Therefore, what about measure of psi C? We have seen that 0 to equal to See, and this is equal to psi of the characteristic. This we have. Okay. Therefore, what you have measure of psi c. Because you see that this is, that is, you have psi empty. That is it. Therefore, this is what. So both psi o and psi c have measure 1. They are non-zero. They are measurable subsets. Psi o disjoint measurable subsets with measure. Measure 1. Okay. So what do we get? Now we look at the scenario. Okay. So you have, this is the interval. I'm using when type. This is C. And then what is called C complement. Okay. So this is this part. And what you have is psi is a map to interval 0, and you have psi c, and you have psi, and this is measure 1. See that? Right? So this is the scenario that you. So C has measure 0. Now what we can say is, by Vitalis theorem, every subset of and is of measure 0. On the other hand, there exists a non-measurable subset of size C. Okay. So W is not measured. Now pull it back. So there is some this is W, not measured. This is not measured. When you pull this back, where does it go to? Oh, sorry, it's not here. I'm sorry. This is sign. Now what you have is that there is a measurable subset of C, psi C. Sorry, a non-measurable subset of C. So W is, see that sine inverse of W is a part of it. Now sine inverse of C and is measurable. With measure 0. What is the result that we are using? Every subset of a set of measure 0 is measurable and is of measure 0. That's the one that we are using. So sine inverse of W is measurable, but W is not measurable. And you see that psi is a one-to-one onto map from here to. Okay. So what do you get? Okay, what is the outcome? So there exists a subset, a measurable subset of C whose image under sign is a non-measurable set. Therefore, there exists a subset of C of measure 0 denoted by psi inverse W in our notation, such that its image under psi that is W is not measured or non so that shows our contention that there exists measurable sets which gets mapped onto non-measurable sets. So one-to-one map. So now we shall make use of this. And what do you have? So we have measure of sine wave of have so the result set. There exists W contained in sort of nice construction of such a set. Right? There are many subsets of a non-measurable Lebesgue measurable set. Of a Lebesgue measurable set with non-zero measure are measurable. That's what we have to do. Now we exploit this result in proving our task that there exists a non-Borel measurable set. So we shall Kumar. Prove that there exists a non-Borel measurable set. Subset of that's our task. How do we do it? It's a fairly simple, straightforward. Thus, so time maps 0, 1 on to 0, 2, which is 1 to 1 on to, and strictly increasing continuous function. We have seen that there exists a C contained in 0, 1 which is mapped by sine onto a non-measurable. This is what we have. we are going to use that. Now we make use of this as strictly increasing continuous function defined on an interval perhaps Borel sets to Borel sets. That means the image of, for instance, psi, you take a Borel set and look at the image of that under psi, it is going to be a Borel set. Okay. Now this can be proved. So use the continuity of by psi to assert that psi inverse of is Borel whenever E is there. What you do is use the fact that the collection of Borel is a sigma algebra containing all open sets. So we use this fact. F inverse of E is Borel. Look at the status of E, where F inverse of E is Borel. Okay. When E belongs to, or this collection of all such sets form a sigma algebra containing all open sets. The open sets are Borel sets. We make use of this result to come to this conclusion. They are very simple statements. Therefore, what we have? So we see that consequently W cannot be a Borel set. Why it cannot be a Borel set? because if it is psi inverse of W see W is a non-measurable subset of psi c. W is non-measurable. So you pull it back. So you take so what is W? W is the image under psi of this is what okay. Psi is a continuous monotonically increasing function, and if W is a Borel set, then what happens? Okay. Right? Yeah. If psi inverse of W is Borel, but and hence measurable. But W is chosen as a non-measurable set. Psi c. So that implies psi inverse of W is not. However, psi inverse of W is I should remove this. This is the argument. W is contained in psi of C. W is non-measurable. This is what about psi inverse of W is contained in C and it is measured. Therefore, what you have is this. This is the argument. Psi inverse of W is Borel means W is Borel. Okay. And hence it is measurable. But W is chosen as a non-measurable subset of psi C, which implies psi inverse of W is not Borel. Okay. So that's the argument. Therefore, it follows that the pre-image of any non-measurable subset of psi C a measurable set to but not a that's how the construction of the Borel set non-measurable what is called a you take psi inverse of W is Borel set but the art of doing it is choose any non-measurable subset of psi of C. Whatever you get cannot be a problem. So now it is time we consolidated whatever we did before we start with the next major topic, namely measurable. Okay, so what have we done so far? Just recap. So, consolidation. So we take R. Now extend concept of length to the concept of outer measure M star for every subset of, that is the first step. What about the next step? So this is our, so the second step is define subsets. Three, show that the measurable, the collection of measurable subsets forms a sigma. And for such sets and for any E okay, then we started looking at this. So for M is a proper subcollection of what does it mean? Showed this by showing that proved this by constructing non-measurable the fifth all subsets of sets of measures are measurable. And have measure every non every measurable set of R with non-zero measure. As a subset is not measurable. Finally, we proved that not every now this is more or less what we have tried to prove. Okay, so the structure that comes out is this is PR, all measurable sets M is contained in this Borel sets. So this is the structure that is proper. That means E is properly contained in measurable collection set of all sets. Now, all these are sigma. This is the measurable class of functions, sets, and B is a subcollection of that, which is the smallest sigma algebra that contains one subsets of. So that is the work that we have done so far, and as I said, without working out problems, you cannot get your ideas. So I hope you would settle down to pick some problems and start working on this subject. But I hope I have given a motivation for defining or extending the concept of lengths for intervals to what are called measure for as large a collection of subsets of R as possible, and these are called the Lebesgue measurable sets. And then the Lebesgue measure is translation invariant and like the length of the interval, and then it agrees with the length of the interval wherever the set coincides with the interval. Okay, thank you very much. So we stop here and we start with what are called measurable functions. Now we start playing the game on this structured set of R by looking at what happens to the functions. And eventually our objective is to introduce the concept of. Thank you very much.